Bobbing up and down on an ordinary spring, this simple weight repeats itself once every second. As time passes, its motion dies down, its excursions become smaller. But it still takes exactly 1 second to make each cycle. It is a perfect time-keeping device, and its motion is called simple harmonic motion. Keeping time has a musical connotation, as does the word harmonic. That's no accident of language. Instruments share a special property with bobbing weights. Both generate vibration at a certain frequency, which produces a certain pitch that doesn't change as the motion decreases. Many factors are at play in the production of musical tone. The length of an instrument string, the size and the shape of an instrument, the technique with which an instrument's played, and certainly the musician's ability to play it. However, in the physics of music, one factor never varies. Once the tone has been produced, the pitch remains the same, even though the vibrations diminish. Why does the pitch remain constant? In the language of classical mechanics, force. The F in Isaac Newton's F equals mass times acceleration. In a certain position, all forces are balanced. However, when the spring is stretched, it attempts to pull the mass back to its original position. The farther the mass moves, the greater the force to pull it back. The same principle works conversely. When a spring is compressed, it tries to push the mass back. Whichever direction the mass moves, a force emerges to counter the displacement. The combination of this force and the mass's inertia will be the key to keeping time and understanding simple harmonic motion. At each point in its motion, the net force is proportional to the distance x of the mass from its equilibrium position and in the opposite direction. The equation is F equals minus kx. The value of k depends on how stiff the spring is. In Western culture, few things govern human life as steadily as the mechanistic concern with time. There are natural cycles. The beating of the human heart. The frozen pace of the advancing and retreating glacier. And there are perhaps less natural cycles, such as the boom and bust of the economy and other things that tend to rise and fall. However, these cycles don't operate under the same laws that govern nature's great clock. They don't oscillate with natural precision. They lack precise intervals, repeating forever, according to an inexorable law of nature. Human imitations of the great clock of the heavens are based on a different but equally inexorable law. Newton's second law states that F equals ma. In simple harmonic motion, this force comes from the displacement, x itself. Force equals minus kx. Together, these two equations give the acceleration of a body in simple harmonic motion. This equation refers not only to a mass on a spring, but to any physical system that, when disturbed, is restored toward equilibrium with a force proportional to the disturbance. The pressure of the air in an organ pipe, or the angle of a pendulum, the bending of a tuning fork, or the rotation of a clock movement. These systems and many others undergo harmonic oscillations. These oscillations can be too fast to see, at least under normal circumstances, or too slow to wait for. Or they can be any other frequency, high or low, all of which can be described by the same equation. A long time ago, someone guessed that the solution may be a sine function. It was an educated guess, because the motion of a mass oscillating on a spring resembles the motion of the shadow of a particle moving in uniform circular motion. So the idea of guessing a sine function seemed quite natural. In this case, a sine function with amplitude A and angular frequency omega. For the mass on a spring, the angular frequency is equal to the square root of k over m. The stiffer the spring, the higher the frequency. The greater the mass, the lower the frequency. But whatever the frequency, it depends on the mechanical properties of the oscillator, such as the mass and the spring constant. The time needed to make a complete cycle does not depend on how big the swings are, represented by A in the equation for x. So even as the oscillations die down, harmonic oscillators continue to keep perfect time. The frequency is measured in radians per second. There are 2 pi radians in each complete cycle. Likewise, in the great clock in the sky, each cycle is divided into radians, as if the universe were an enormous circle. To an extent, it is. The natures of uniform circular motion and simple harmonic motion are closely related. Each clock, in its attempt to duplicate the cycles of nature, is a mere shadow of the cosmic clock. When any harmonic oscillator is disturbed, the disturbance produces a force that pushes it back to where it was. There, the force is 0. But inertia keeps it going until the reverse force stops it and pushes it back once again. This is the essence of harmonic motion, a simple harmonic oscillator. If it were really simple, it would go on forever, a perpetual motion machine. But real oscillators are not simple. They always have other forces, friction, air resistance, and so on, that tend to make them slow down. That's why, from time to time, clocks must be wound or have their batteries changed. Friction turns energy into heat. That energy must be restored in order to keep the clock going. But even as the clock winds down, the period of time for each of its cycles remains constant. With harmonic oscillators, clockmakers were able to introduce accuracy and uniformity to timekeeping. An hour in Cambridge became precisely as long as an hour in Venice. Harmonic motion can be found in an enormous variety of physical phenomena. Understanding it helps to explain the subtle unifying principles that govern the universe. But what happens when an object is disturbed not just once, but repeatedly, with a force that oscillates with a given frequency? Here's another oscillating system with a natural frequency. In fact, the child and the swing are a kind of pendulum. A slightly larger mass, this one with longer legs, has learned to provide her own periodic push by shifting her body weight, kicking forward as far as possible, and tucking her legs under. Correctly applied at the same point on each cycle, this young swinger displays her mastery of the phenomenon of resonance. There are many things in our daily life which indeed exhibit resonance. Certainly music is, or ought to be, a pleasing example of resonance. Buildings between 5 and 40 stories tall are typically resonant at earthquake frequencies. Only by strict adherence to earthquake-building codes can a structure resist being ripped apart at its very foundations. Not exactly the sound of music. But these sounds, produced by wires in the wind, are another effect of resonance. How do the wires create this eerie song? By vibrating at their natural frequency. The airflow dynamics around a taut wire create some rather complex patterns. In high winds, the normally stable airflow around a cylinder, such as this wire, becomes unstable. As the wind tries to close up the gap on the downwind side of the wire, to prevent a vacuum, eddies start to form. Soon, the eddies start peeling off and running in the downstream wake, creating a complicated but stable flow pattern. Every time a vortex peels off, it gives the wire a little push. At a certain wind speed, the vortices start peeling off at the resonant frequency of the wire, setting it into motion. This effect is called an aeolian harp and accounts for the strange sounds of telephone wires vibrating in the wind. The Tacoma Narrows Bridge, perhaps the most spectacular aeolian harp in history, opened in July 1940. It was one of the longest suspension bridges on Earth, but it wasn't destined to be around for very long. Even in a light breeze, ripples would run along the bridge. On November 7, 1940, just 4 months after it was opened, the winds were relatively moderate, about 40 miles per hour. The bridge started to twist violently, and at 11 a.m. it collapsed. Simple harmonic motion is nature's response to twanging any stable system. And resonance is the large increase in vibrations of a system when a driving force is exactly the same frequency as the natural frequency of the system.